When you place an object on an inclined plane and very gently, gradually lift the incline, you can make it steeper and steeper and make the angle greater and greater and have the object that's resting on the incline stay at rest. Now, once you go past some maximum angle, then that object's going to start to slide because you break frictional welding and the component of gravity pulling down the incline exceeds the maximum available force of static friction. Okay, well, you can determine what the coefficient of static friction is simply by calculating the tangent of this angle. It's that easy. Coefficient of static friction is equal to the tangent of the maximum angle for which an object on an incline remains at rest. There's a proof for that. Gravity pulls straight down. The normal force points perpendicular to the incline. And the force of friction holding it at rest points back up the incline. All of these forces have to be in balance such that it represents static equilibrium. Now, we can't appreciate that real clearly until we break the weight vector into components. So let me draw a second resolved free body diagram. So the normal force is fine as it is. The friction force is fine as it is. We'll call that F subscript S to remind us this is static friction. So there's a component of gravity, as you know, that points perpendicular to the incline and is calculated as mg cosine theta, and the component down the incline that's calculated as mg sine theta. Okay. Well, the forces along the y-axis have to cancel one another out, as do the forces along the x-axis. So let's make a statement about the x-axis. The force of static friction has to be equal to mg sine theta. From what we see on the y-axis, the normal force has to be equal to mg cosine theta. And it turns out that a force of friction is always equal to the product of the coefficient of friction times the normal force. Well, actually, when it comes to static friction, the object will remain at rest at a very low angle, and again at a higher angle and a higher. There's many angles for which the object will stay at rest. Static friction varies from 0 up to some maximum value. So we could say static friction is less than or equal to this coefficient of static friction times the normal force, or another way we can say it is the maximum force of static friction is equal to the coefficient of static friction times normal force. Okay? So since we're doing an experiment in which we're going to find the maximum angle at which you can place an object on an incline and have it stay at rest, we can use this equation. And if we apply this equation along with these equations for equilibrium independently stated for the x and y axes, we can make some substitutions. For example, let's make a substitution for the statement about the x-axis. The coefficient of static friction multiplied by the normal force is equal to mg sine theta, right? We've just replaced static friction with mu times n. And then n happens to be equal to mg cosine theta, so we can make that substitution. So the static coefficient of friction times mg cosine theta has to be equal to mg sine theta. I think you can see where this derivation is going. Divide both sides of the equation by m, divide by g, it all cancels out, and we divide both sides of the equation by cosine theta, and we find that the coefficient of static friction then is equal to sine over cosine, which indeed is tangent theta. But let's be careful. We can't just come up to any incline, place an object on it, and say, ooh, aha, the object is at rest. Let me measure that angle. The tangent of that angle then must be the coefficient of friction. No, no, no. You have to go through the exercise of finding the maximum angle for which the object stays at rest when you use this equation, right? So coefficient of static friction is equal to tangent of theta subscript maximum static, right? It's a special angle that you have to take the tangent of in order to calculate the coefficient of static friction. Likewise, you can carry on this experiment and find out at what angle will the object slide at a constant speed. And it turns out that angle is always a little bit lower. So if you find the angle for which it stays at rest, and then you back that angle down just a little bit, then the object stops accelerating down the incline, having broken frictional welding, and just proceeds with a constant speed down the incline. So still, that means acceleration is 0 if the velocity is constant, which means the net force has to equal 0. And the free body diagram in this case looks identical. Normal force this way, a component of gravity opposite the normal force, a component of gravity pulling the object parallel to the incline, and if the velocity is indeed constant and the acceleration is 0, then the force back up the incline of friction is just as large in magnitude as mg sine theta. It's just that we don't label it F subscript S for static. Now we label it F subscript K for kinetic. Now when it comes to kinetic friction, as you recall from a graph that we illustrated in a previous lesson, there are two ranges for this graph where we compare applied force to frictional force. In the static range, the force varies from 0 up to a maximum value, but once you go past static, or a condition of being at rest, to the case in which an object is sliding, then the force of friction drops off to a constant value. So we don't state an inequality, right, that static force of friction is less than or equal to mu static times normal force. When it comes to sliding or kinetic friction, it's a strict equality. Force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So static friction has a range from 0 to a maximum, so the equation involves an inequality. Sliding or kinetic friction is constant, so the equation is strictly an equality. Okay. Well then, this force of kinetic friction must be equal to mg sine theta, and the normal force must be equal to mg cosine theta. That's the only way forces in opposite direction cancel one another out. So let's restate this, making this substitution. The coefficient of kinetic friction times the normal force, that itself is the force of friction, must be just as large as mg sine theta. But normal force can be substituted with mg cosine theta. So mu kinetic times mg cosine theta equals mg sine theta. So once again, mg cancels out. We divide both sides of the equation by cosine theta, and the coefficient of kinetic friction, that's sloppy work, isn't it? Let me slow down and write a little neater. The coefficient of kinetic friction is equal to tangent theta. But wait a minute, tangent what theta? This again is a special angle, right? You can't just walk up to an incline, measure its angle, and say, oh, the coefficient of sliding friction for that ramp must be the tangent of that angle. No, you have to put an object on that incline. And if you find that tapping the incline in order to break frictional welding at this particular angle results in speed that's constant, well, then that's the angle you're looking for. But any other angle doesn't cut it. So we'll say this is the tangent of theta, what do we say? Constant. Okay, good enough. So there are two special angles that you can find by experiment: the angle for which an object will slide at a constant speed, the slightly lower angle, and the angle for which something will remain at rest due to frictional welding. Taking the tangent of either of those angles is a way to calculate either the coefficient of kinetic friction or the coefficient of static friction.